Welcome back to the Ephemeris podcast. I'm your host, Ophelia, and thank you for joining me on the 21st episode of Season 2 regarding cosmology on this astronomy podcast. Today, we have a huge episode, and I mean huge, because as you probably know, we are talking about Isaac Newton. You've heard his name, but maybe not his story, and likely not much about the specific work that he did with celestial mechanics, so I'm here to talk all about it. But first, as we always do, we should begin with some background about Newton himself. Newton was an English mathematician, physicist, astronomer, you name the science, that's him. Not really, but you get the point. Cool fact, he was born on a Christmas day in the old Gregorian calendar, but we know his birthday to be January 4th in the new one. He was also born prematurely, which is like a fact that gets brought up in a lot of the biography articles about him, but I don't know, you decide if you wanted to know that or not. Newton attended Trinity College in the University of Cambridge, and some way, somehow, the college was still teaching about Aristotle when it came to philosophy and teaching all this geocentric stuff and, ideas of like what is natural motion and all that stuff. But he did end up studying more new faces with some more advanced ideas about science, like Galileo and I believe his name is Descartes. I forget how to say it. I know I looked it up one time, but I completely forgot what the correct pronunciation of his last name is. Anyways, that's besides the point. So college is where Newton begins to pick up things like calculus and optics and a teeny pinch of physics. In fact, he worked on all three of these things even as college was closed due to the bubonic plague. And I bet that makes you feel quite useless when you remember what you did during the COVID pandemic. At least it makes me feel useless. But different times. Anyways, this is where Newton's work begins to branch off. He does a multitude of different things regarding science, but given we are an astronomy podcast, we will focus on the pinch of physics first, and then we will leave off with some remarkable works of Newton that were in other fields. So, here we go. Newton's work in physics is rooted in the curiosities he addresses in certain philosophical questions. Now, a lot of his works were titled in Latin, but I'm going to give the English translation to those titles, as I do not want to make myself pronounce Latin. One Latin name that I will preserve is Principia, which is usually how we refer to his work. What's it called? The Mathematical Principles of Natural Philosophy. So yeah, let's get on with his first work. It was written in 1664, and it was initially notes that he took in college about Aristotle, but he began to add notes about Galileo and, the radii of stars and metaphysics, so some more recent and relevant ideas. He also, and keep this in mind for sure, made notes about a comet on December 9th, 1664. He took notes on his reading of Galileo's Two Chief World Systems piece, which we have talked about previously, where it was pretty much just a half-hearted attempt by Galileo to not get scrutinized by the church, but Newton ended up reading it anyways. As put perfectly on the internet, the notes began with the nature of matter, place, time, and motion, and went on to the organization of the universe. This was followed by what could be classed today as properties of condensed matter, for example, rarity, fluidity, hardness, etc. These were followed by questions on violent motion, light, color, vision, and other sensations. Another cool non-astronomy thing to quote or kind of cite here. The then current theory of color held that white light was elementary and that colors arose from mixtures of light and dark. Newton criticized this theory by noting that in that case, a printed page with its juxtaposition of light and dark would look colored. In Folio 122, he recorded for the first time his notion that white light is heterogeneous and colors arise, not through a modification of a homogeneous white light, but from the separation of this mixture into its components. So, this being said, you can give the credit all you want to Kepler for being the founder of modern optics, but Newton founding the fundamental ideas of spectroscopy, you could say, might give that idea a run for its money. So that's all the stuff we have going on in 1664 for Newton. Quite a lot of optics in there, as has been mentioned before, and a little bit about astronomy. He spends his midlife working with, I think he was either working kind of coincidingly with Leibniz, or he was working with, I forget which one, but he was working on calculus nonetheless, and did some work with infinitesimals and whatnot, which is going to come into the story a little bit when we talk about Principia. Other things that he did in his life, he observed that a prism refracts different colors at different angles and gave the spectrum its name as a part of his stuff with optics. I'm not going to keep saying, work on optics. It's going to be very obvious that a lot of his work is on optics. He also created a functional reflecting telescope. I believe it was 1688, or was it 1668? It was 1668, and discovered chromatic aberration. But then in 1679, he revisited celestial mechanics. And this is where the fun stuff happens, so buckle in. In 1680 and 1681, he observes a comet, and this gets him inspired. And he starts working with John Flamsteed. Sounds like a familiar name, doesn't it? But he's also in works with Robert Hooke, a little bit, only a little bit. There was quite a lot of bad blood between Hooke and Newton, but in this period of time, 1679 to 1680, they were working together out of necessity. So while he was working with him, Newton created a proof that the elliptical form of planetary orbits would result from a centripetal force inversely proportional to the square of the radius vector. Now, there could be multiple ways to analyze what exactly this statement means. If we take it from the perspective of fundamental centripetal motion as we understand it today, it's not exactly true. Centripetal force is inversely proportional to the radius, not squared, and proportional to the squared velocity. And additionally, the most fundamental forms of centripetal motion lead to circles and not ellipses. However, this is very unlikely what Newton meant, because there's a different law that he created that brings validity to this statement. It's his law of universal gravitation, where the force between two comparable masses is in fact inversely proportional to the radius squared. So, yeah, there you have it. The proof established in Newton by Newton in 1680 and exchange with Robert Hooke reveals that this is the moment he realized the universal law of gravitation. So that's pretty neat. In 1684, some of the work that Newton had done on celestial mechanics was communicated to Halley as well. And if you'll remember my mentioning of Halley being really interested in receiving Newton's work, this is where that whole story begins. Newton sent on the motions of bodies in an orbit to Halley containing the core of Principia, otherwise the mathematical principles of natural philosophy. This work that he sent to Halley contained the solution to Kepler's problem, the mathematical derivation of Kepler's 3 laws of planetary motion. So when I tell you that Halley's career was truly full of opportunity, I'm not saying that as an exaggeration, because never in a million lifetimes could you expect to personally be sent some of the greatest scientific work of all time. Like Principia is considered to be the scientific works of all time. So yeah, I'm not exaggerating when I talk about Halley's career being truly blessed. But anyways, Halley did his part in encouraging Newton to publish the work that he was sent in 1687, and he helped finance it and all that good stuff. But we're not here to talk about financing. We're here to talk about the astronomy that is contained in the manuscript and what's in the Principia. So let's get right into that. De Motu, which is the abbreviated Latin name of this work, contains 4 main theorems with a couple of important definitions and hypotheses. Firstly, Newton defined the centripetal force as impelling or attracting a body to some point regarded as a center. He establishes what he calls an inherent force, which isn't exactly accurate, but hints at the idea of inertia and kind of leads into his establishment of the first law of motion. And then the last definition of importance that's in this manuscript is resistance, which is some property of a medium that impedes the motion of an object. So yeah, those 2 last definitions are mainly significant because of their hinting at inertia. As for his hypotheses, one of them is plainly the first law of motion. The intrinsic forces of an object alone will keep it in motion forever unless something stops it. And inertia, in complete fairness, isn't a force, but the idea of no forces acting on an object is what is significant here. The next hypothesis was Newton's way of saying you have to treat forces like vectors. He established sort of this parallelogram rule or concept, but really it's just his way of treating forces like vectors. The last hypothesis says that just as a centripetal force is acting on an object, the distance it travels still follows the laws of projectile motion, which we talked about with Galileo, sort of distance being proportional to time squared. So let's move on to the theorems, as those are the last of the hypotheses and definitions. The first theorem that Newton argues in this manuscript is that the radius vector drawn from the center of orbit to an object that's orbiting, when there is a centripetal force, sweeps out equal areas in equal times. And notice how that sounds a lot like Kepler's second law. Also, just as a quick note, justifying this theorem requires infinitesimal calculus, so this is kind of where that stuff comes in. So that's a little cool. Newton's second theorem is basically F equals mv squared over r, which is sort of the rule for centripetal forces, except he didn't have the m in consideration because obviously his ideas of inertia were not completely solidified by that time. But the third theorem gets juicy because here Newton begins to explore the idea of non-circular orbits. To do this, Newton ends up using infinitesimal calculus again and kind of drawing infinitesimal arcs, but here's what it all boils down to. In the case of an elliptical orbit, Newton looks at centripetal forces at the foci and finds that they will be inversely proportional to the squared radius at these points. And there you go. We have an even better explanation as to the justification of elliptical orbits in the universe. Not just, intrinsic velocity and kind of the dynamics between the sun and the planets, but also the resulting changes in forces. Then comes Theorem 4, where Newton says that if an orbiting object has enough velocity, it will escape a circular or elliptical orbit, or essentially a circular or elliptical orbit won't be possible, and the object will instead follow a parabolic trajectory. And he mentions that this will be the case during an object's motion in the atmosphere without significant air resistance and the fall of heavy objects. So that's basically what's a part of the De Motu manuscript, and these will be the contents of the first and second book of Principia. Book 3 of Principia, after these two that are based on the manuscript, this book 3 begins to concern astronomy very specifically. I know it's been quite a lot of fundamental physics, but we're getting back to astronomy in the end. He talks about the variation in the orbit of the moon and the inverse square law applying to all planets orbiting the sun, and inverse square law being what we talked about previously. However, we see some contribution to this book by Halley and Flamsteed in the form of theories about comets. Newton also uncovers theories about axial precession, which has been measured, as we've talked about across the season, but probably not theorized as much. And he gives an explanation for tides being caused by the moon. Last thing, and at no surprise at all, Newton claims his support for the heliocentric model of the universe. There are times in which he considered that the sun and the planets might not be at rest, but kind of going at a constant velocity in some direction through space. However, he leaned towards the at-rest proposition in the end. So yeah, that is the essence of possibly the greatest scientific work of all time, and possibly the greatest scientist of all time, Isaac Newton. There are some other great works by Newton, one namely aptly named Optics, which refutes the idea that light is fundamentally white, as we've already talked about, his 1664 work having a little bit of that notion in there. But yeah, that is pretty much the man, the myth, the legend, Isaac Newton. And hopefully you all enjoyed hearing an in-depth explanation about the celestial mechanics work that Newton did. If you did, I would sincerely appreciate a subscribe on YouTube or a follow on Spotify, depending on where you're listening. And until the next episode, I will see you all later. Peace.